All right, so for this one, we have and you're going to need to add this to your packet. We have a salt conveyor cart moving horizontally, and it's going at a constant speed, and salt is poured on it to it at zero point 0.2 kilograms every second, and we want to find out how much force is needed to keep it moving at a constant speed. So let's go ahead and draw that, and we've got the cart moving from left to right here, and we've got the salt that's being poured in. And so, yeah, we want to figure out how much force is needed. Now, you do need to know a few other things. You need to know how fast. So let's say it's going at 2 meters per second. Um, so yeah, go ahead and pause the clip and figure out how much force is necessary here. And then when you're ready to check, you can hit play to continue. All right, so MV final minus MV initial. We know the final and the initial are the same. It's both 2 meters per second. The question here is what to do with mass. And it turns out what you could have done is chosen any mass. You could say it's 5 kilograms initially, and then here, and then say finally it's 5.2, or it's 10, and then 10.2. And then the time would be 1 second. And then yeah, you'd have everything you need. I just started with 0, and then finished with 0.2. Again, you could have chosen anything there, and it should take 0.4 newtons of force. So the second part of this is how much force is needed to keep it going at 4 meters per second. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so it's going 4 meters per second, and therefore, it's going to take more force. It's going to take 8 newtons. Now, this seems to violate Newton's first law of motion, which states an object in motion will stay in motion at constant speed as long as there's no net force. Well, there's a net force here, right? We got a force, and it's going at constant speed. But what's happening is the mass is changing. The mass is increasing, and because of that, we do actually have to have a net force. Now, if you remember with conservation momentum, we say that the momentum is conserved as long as there's no net force on the system. So in other words, if there's no external forces, if you have 2 carts that collide, and then hit, as long as it's just those 2 cars, that's the system and momentum could be conserved. But if you have an outside force, coming in, like pushing the cars, if these were toy cars, that'd be an external force. Similar here, let's say, you got a cannon, cannonball is shot, and, the cannon recoils back. Well, as the cannonball is shot, and then the cannonball recoils back, or the cannon recoils back, sure, momentum's conserved. However, what do you have on the ground? You have friction, right, which slows the cannon, and it's not like it's a frictionless surface and it keeps flying back, right? So that would be an example of an external force. And so internal forces arise inside the system. That would be, the combustion of the gunpowder inside, and then the combustion of the gunpowder inside exploding, and then the separation between the cannon and the cannonball. But as soon as you look outside, you're going to have external forces. For instance, too, on this projectile, which is a cannonball, you're going to have the force of gravity on it. It's going to change the momentum of the system. So in golf, right, you hit a golf ball with a club head, and that's an external force on the golf ball. So that's going to change the momentum of that golf ball. Now in pool, though, right, if you just got those 2 pool balls and, they hit, momentum can be conserved, and that's a collision that we can use conservation momentum with. So remember, with conservation momentum, it's all the initial momentums equal all the final momentum. On your equation sheet, you do not have this. They expect you to know that momentum's conserved starting and finishing with the same amount, and so you do need to memorize that. Let's go ahead and try this one as we get started with practice with that. We have a man sitting in the back of a canoe that's at rest, and the man begins to move forward. What happens to the canoe? So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so initially their velocities are 0, both are 0, and then we're looking for the final. We know the mass, we know the final velocity of the man is positive 0.5 if you set up the man as going from left to right. So therefore, the canoe's going to go back, and the reason that the speed is less is because it has more mass. The canoe itself has more mass. All right, now on this one, we're dealing with an exploding casing, and it's breaking into 3 fragments, so we can draw that. Fragment 1 we'll say is going up northward, and then we have fragment 2 going east. The question is, what is fragment 3 going to do? Well, what's important in this one is to look at the momentum in the x and y separately. And if you remember, we have to look at conservation momentum in the y, so y momentum, and the x momentum separately. And if you look at mass 1, they're all v initial is 0. v1 initial is 0, v2 initial is 0, v3 initial is 0. But v1 final is positive, which was that north, positive 200 meters per second, right? So it's going upwards at 200 meters per second, but that's just in the y. Just in the y here, not in the x. In the x, there's no velocity, so in the x, v1 final down here is going to be 0. So yeah, go ahead and give this a try and solve for what mass 3 is going to do. And when you're ready to check, you can hit play to continue. All right, so we have our y momentum, negative 133.33 after we solve for it. And then for our x momentum, our positive, actually both of them are going to be negative 133. So over and down, and both are negative, and so we should get a resultant of 188.56, 45 degrees south of west. And that's just because in this one, it turned out to be the same. Won't always be that way. All right, so for this one, second test, and we can draw these out. Let's call mass 1 the one that flies off to the left, mass 2 the one that goes down, and mass 3 is what we want. What happens to it. So go ahead and pause the clip and give this one a try and see if you can find the resultant for mass 3. And when you're ready to check, you can hit play to continue. All right, so for mass 3, for the x momentum, we should get positive 128.57. For the y, positive 92.14 for a resultant of 158.18 at 35 degrees, or 35.63 degrees north of east. Or the reciprocal of that, whatever, that would be 54.47, I believe, east of north. All right, so if you remember with collisions, right, collisions come different types. Elastic, there's no kinetic energy loss. We look at those with like the magnet carts last year. Inelastic is the most common that we usually see, where things hit but they separate. And then perfectly inelastic is where they hit and they stay together. So let's go ahead and do this one here where the 2 cars hit and they stick together. And we have a 1,500 kilogram car going to the west at 25 meters per second. It hits another one going to the east at 7. And when we want to find the final velocity, that's the first part. And then the second part is we want to find the loss in energy, where we look at the energy before, the energy after. So yeah, go ahead and pause the clip and calculate the final velocity. Remember, this is going to be the same. They're going to stick together. So v final would be the same, and you can factor that, and then you can get the energy. So yeah, go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so we should get negative 8 meters per second. The key here is with the car that's going west has a negative velocity, if you remember how important the signs are in this unit. And then for our energy, we can look at the energy before, which is 510,400. Afterwards, it's 102,400. A loss in 408,000 joules. And head-on collisions are rough, right? Because you're going to lose a lot of energy in that collision.